Hello and welcome to this video on momentum. Specifically today we're going to be talking about impulse. What is it? How do we calculate it? And how is it relevant to us? Last time we started by talking about Newton's three laws of motion. We talked about how an object in motion will stay in motion and an object at rest will stay at rest unless acted on by an outside force. And we talked about how this is a momentum. What we didn't talk about is this section right here. Unless acted upon by an outside force. The outside force which causes changes to your momentum is what we refer to as impulse. Impulse, in short, is a change in momentum. It's mathematically represented by the letter J. Why? Because I has been used for intensity. And the easiest, simplest way to think about it is delta P, your change in momentum. Now, this is a vector, it has a little vector hat on it because the direction of the change matters, just like momentum's direction matters. Occasionally, you'll also see it as m times delta v. This assumes that the mass of the object doesn't change, just its velocity and the direction of its velocity. The final and most directly relevant to the definition form is F times delta t. Until a force acts on it, and the force has to act for a period of time. This actually brings us to an interesting point. Because it's force times time, that's a Newton times a second. And if you remember, a Newton is a kilogram times meter over second squared. If you multiply that by a second, this second cancels out and leaves you with kilograms meter per second. Which is why the other unit for momentum that is often used in the SI community is Newton's second. So let's take a look at some examples. The easiest way to talk about this is a ball bouncing off of a wall. In this case, the velocity initial is 10 meters per second to the right, and then the velocity final is 15 meters per second to the left. The change in velocity here, final minus initial, is -5 minus 10. I'm using -5 here because I'm using the standard assumption that left is negative. If I wanted to say right was negative, it would be positive 15. So in this case, my delta V is -15. If I want to talk about my change in momentum, well, I need to know the mass of a tennis ball, 0.145 kilograms. So my momentum goes from 1.45 newtons second right, and it would end being negative 0.725 newtons second left. In this case, 5 times 0.145, 10 times 0.145. My change momentum, my delta P, would be this final minus this initial. I used a negative sign here for left and right. Again, calculate. Negative 2.175 newtons times seconds. Had I just taken the 15 and multiplied that by the 0.145, I would also get the 2.175. In other words, I can take the P final minus P initial, which is delta P, or I can use the M times delta V. Go ahead, calculate case B on your own. All right, if you went through and did the math carefully, you should get 8.41 negative newtons times seconds or kilogram meters per second. In the blue here, I calculated the delta V, and then I went through in the green and solved it that way, m times delta V. In the black here, I went through and calculated the initial momentum and the final momentum and calculated the difference between them. Now, you'll notice that even though the speed change here is larger, from 10 to 5, the momentum change and the velocity change is much larger over here because of the direction shift. If this was going 30 right to 28 right, there would be a very small change. But because you're changing directions, the change in velocity is very large because direction matters. because direction matters, because the velocity changes, your momentum changes also larger than you had over here. All right, final thing. We talk about how it can be applied to force. So let's go ahead and do one of these with a force calculation added on. A 350 kilogram car is traveling at 10 meters per second squared. The driver steps on the gas, applying 490 newtons of force for 7 seconds. What is the new velocity? We could do this as a kinematics problem. We know the net force, we know how to find the acceleration from that. We can then V initial, V final. But we don't have to go through all the steps. We have this giant equation. The AP exam, for those of you who are taking the AP exam, only will give you these two equations, but they're enough to get us there. In this case, we know the mass, we know the initial velocity, we know the time, we know the force. All we need is our final velocity. In other words, delta P equals F times delta T. Or mv final minus mv initial equals F times delta T. If you want to solve this all on your own right now, go ahead and pause. I'm going to keep going. I'm looking for the V final. So mv final equals F times delta T plus mv initial. V final equals F times delta T plus mv initial over m. Plug in all my numbers. I will get 490 times 7 plus 350 times 10 over 350, which equals 19.8 meters per second. I can also solve this numerically, at which point I would just use this section, 350 V minus 350 times 10 equals 490 times 7, 350 V minus 3500 equals 3430, 350 V equals 6930, which when I divide over gives me the 19.8 meters per second. And there you have it, that's impulse. Now, we can also talk about impulse applying to a system, at which point the same process we did on the previous video would also work. You could go through and calculate the total momentum of the system and then talk about the change of each of the components in the system, or the total change of the system. But it's the same general process we just did right here. As a reminder, these are the equations that the AP exam will give you and not much else. Anyways, thanks for watching. Have a good one.